That's streaming sponsors. Just speaker. We got on just speaker, and we are going and we're recording. Thank you very much. Sorry for the inconvenience.
No problem. Okay, we'll get started then. Let's make sure this is working good. I am Dr. Whom, or Nathaniel Husted. Find me at NW Husted on Twitter. I will be talking about emergent vulnerabilities, as well as what ant colonies, schools of fish, and InfoSec have in common. So let's get on with a little bit of introduction. So you at least believe that I have some expert knowledge in what I'm going to be talking about today. I am a PhD candidate right now at Indiana University up in Bloomington, primarily security research. And I'm a bit of an industry wannabe. That's where I'm going to end up when I graduate, and why I love seeing everybody here at DerbyCon every year. So the things I do on a day-to-day basis for work, right now I like to call it postmodern cryptography is what pays the bills. I've been working on a secure two-party computation system. I've done a little bit in fully homomorphic encryption. I've done a little bit of mobile device security R&D. And my personal research, my dissertation, what I'm going to talk on today, what I'm passionate about, is I kind of want to figure out what vulnerabilities are going to look like in 5 to 10 years from now. So a little bit of InfoSec futurism. So of course that leads us to ask, what are they going to look like in 5 to 10 years? We certainly make some predictions. I'm not going to say for sure my predictions will be correct. I think we're going to start seeing emergent vulnerabilities in the next 5 to 10 years. But like any futurism type prediction, it can be hit or miss. So before I go into the specifics of emergent vulnerabilities, I want to argue for why we're going to see a new type of vulnerability show up in the next 5 to 10, maybe 15 years. And that's because mobile devices have radically changed how we interact, both socially and digitally. My first question here is, how many people when you walk down the street do you see with a smartphone in their hands, writing a text? Well, I'm on a college campus, so everyone under the age of 22. Everyone, just constantly. How much of your personal life is stored on that small screen that you keep in your pocket? For most people, everything now. You can do banking on it. You've got your personal photographs. You have all your contacts. You pretty much have almost all your PII on that device. And it even has a faster internet connection than your home broadband. Most people, not everybody. At least in my area, mine's about twice as fast. My opinion on all this, then, is because of the way these mobile devices have changed how we interact. We've gone from net consumers to net producers of content on the internet via YouTube, social networking websites, Twitter. We're no longer consuming information primarily consuming information written by a New York Times reporter. We're producing all this content. We're sending out tweets, we're putting Facebook posts. We also now have this attachment to the physical and the digital with these mobile devices. For example, wearable computing, Google Glass. You have a computer hooked up to the internet that is basically going to be able to broadcast your visual cortex to the whole of the internet. Everything you see, you can now post online on YouTube. And it also provides digital information, context-specific digital information, in regards to augmented reality. You can use your physical location, it knows where you are. We can use it to digitize every moment of our life now. And we also have the Internet of Things on top of all this wearable computing. We've already heard 3 talks as of today that I think nailed home this point. We had the keynote by Ed. We had Razor's talk and Asobi and Hectaman's talk today, all about these physical interacting entities we're connecting to the digital realm of the internet. And this collision between the physical and the digital have created this new type of vulnerability that I refer to as emergent vulnerabilities. And the reason this has happened is because now we have all these this digital portion of our entities allows ease of interaction, constant interaction. The physical portion also brings in some norms of social interaction, some elements of social interaction. And so we have vulnerabilities that will now emerge from all these complex interactions in our socio-technical systems. And to be clear, a socio-technical system is really just, in this case, our devices, their interactions with other devices, the other devices interacting with other people, you're interacting with your device, you're interacting with other people, et cetera, et cetera. And all these interactions eventually allow some complex phenomena to emerge. And don't worry, I'm going to get into the details of these exact specific definitions. But don't think of this as FUD. I consider this more of a concern, uncertainty, and doubt regarding emergent vulnerabilities. And that they're going to be a problem, but we don't currently have well-defined definitions, frameworks, and set of tools for analyzing them. I'm going to try and talk about a few today in this talk. And the folks who are studying them don't always use the same terminology. That's why later in this talk I'm going to give you a firm definition of an emergent vulnerability, give you some examples. Hopefully then we can all start working on the same page. And the reason I call this CUD is they probably won't cause a nuclear facility to blow up, but they're going to cause huge amounts of privacy violations, which, depending on your views, could be just as dangerous. You're probably not going to see them coming because they're emergent phenomena. And these problems are only bound to get worse as we have even more devices showing up, more devices being interconnected. So we have a lot to cover in this talk. What I'm going to do is I'm going to provide a little bit of a background on complex systems. What that will allow is now, by the end of that, we'll all have a firm grasp of what the heck I mean by emergence. We can then start talking about a definition for what an emergent vulnerability is. I'll provide an example of an emergent vulnerability, and then I'll close with some open questions I have about emergent vulnerabilities. Maybe some folks in the audience will have some ideas, and at least problems that we can work towards to solve in the future. And I will actually tell you what fish and ant colonies have in common with InfoSec. Don't worry. So let's go. Part one, complex systems. Well, a system is a set of things that interact. So, like a car engine, it's a lot of parts that interact. But a car engine is not a complex system. Same with a laptop, lots of parts that interact. But they don't quite match the definition of a complex system quite yet. In this case, in both the engine and the laptops, it's because their interactions are completely deterministic. One part leads to an action of another part in a nice long line. So then, what is a complex system? Well, in the academic community, there's a lot of different papers where this is argued about. But I have a few ideas from trudging through a bunch of the literature, a lot of a little philosophy about the characteristics of a complex system. So we'll go through a list of these characteristics. The first one is a complex system has to exist in an environment. Think of ants in an ant farm. They exist within the ant farm, they can interact with the ant farm, that is their environment. They also have a large number of components. So we have this idea of a large number of fish in a school, a large number of ants in an ant colony. But we don't want too many components. So, for example, molecules in a jar of water, too many components. We can use something called statistical mechanics to figure out properties of that. When it comes to schools of fish, statistical mechanics falls apart. For those who are familiar with the game of life, a complex system has to have all its components interacting independently at the same time without central control. That's, of course, why car engines fall apart. They're linear interaction. Each part isn't acting at exactly the same time. They're all acting in alignment. And then these simple interactions in the system have to lead to increases in organization. So, for example, think of schools of fish, very simple interactions between all of these fish, and suddenly they can form together in some very complex structures, which this would be a nice school of fish there. And they also lead to emergent behavior. So, for example, the whole cellular automata thing, this isn't showing up quite clearly. You can have very simple rules that show up very complex patterns from just saying, well, is my neighbor on or off? And finally, these interactions allow the system to adapt and evolve to its environmental changes, just as human society over the years so human society is a complex system. We've adapted to changes in our environment. So now here's two very clear examples. Think of a swarm. We can have each of these, just depending upon the position of their neighbors, move from in originally a complete random order to suddenly following a very orderly, swarm-like single direction. And this isn't centrally controlled. This is every little triangle, every little bird in this flock, just paying attention to what its neighbor's doing. Ant colonies are the same way. There's actually a really great TED Talk on ant colonies. And the really cool thing about ant colonies is each ant acts independently. There's no central general ant. The queen ant doesn't control everybody. Each ant, talking with its other ants, figures out what job needs to be done right now in the colony and goes and does it. There's no central government structure. So now that we've talked a little bit about complex systems, this idea that a complex system is a bunch of parts acting independently, interacting with each other, from those interactions we can get some very complex emergent behaviors or self-organizing behaviors like a school of fish. We can talk about an emergent vulnerability and how we can now tie in vulnerabilities with a complex system. So if we look at this wonderful wall of text, we have traditional vulnerabilities on the right. This definition is from the book on computer security by Matt Bishop. It's a property of a device, it's software, it's hardware, or it's administrative procedures that causes the system, your device, software, hardware, to enter into a vulnerable state. So, ODay, that takes advantage of a vulnerability, causes your software to enter into a vulnerable state. Now, emergent vulnerabilities are a little bit different. And to show you, sort of blow out that difference, so as I said, traditional vulnerabilities are of a device, it's hardware, a single property. A complex system is the properties we look at for an emergent vulnerability. It does not affect specifically just a piece of software hardware. It affects a complex system, this complex socio-technical network of all our devices interacting. And it causes one or more of those elements of a complex system to enter a vulnerable state. It's not a flaw specific to those devices. It's something that extends from the interaction of all these devices with each other. But the other problem is it only occurs when this complex system, our socio-technical network, is in a specific state of its own. I'll be getting to an example shortly to really illuminate the wordy definitions. But as an overview and summarization of those definitions, traditional vulnerabilities stem from errors. But emergent vulnerabilities stem from our device interactions and not errors on those devices. It's taking advantage of complex behavior. And what's so special about them is, as I mentioned, you can have security systems completely secure, but they can still have an emergent vulnerability. And you can't really find these during code analysis. You can't perform static analysis, an application analysis on a code body and determine if it has an emergent vulnerability. You have to see them interact. And that's why probably a pen test won't pick this up either, because you need a large number of things interacting, something you're usually not going to be able to recreate without things getting very expensive. And they don't require, as I mentioned, software and hardware flaws. So phrases that I've seen before is Eugene Spafford had mentioned back in the late 80s, emergent faults. So an emergent fault, similar to an emergent vulnerability, but in this case, it's a system fault caused by how configurations interact. And then emergent misbehavior is some work I've seen from the formal methods community, which says we can have this awesome complete system spec for our giant airplane, but there's some complex interaction that we don't yet understand that suddenly will cause a part of that airplane to fail, even though we've proven everything else to be mathematically correct. And of course, if we do have software and hardware flaws in our devices, it certainly doesn't make this stuff easier. So what's difficult about researching these and finding them is, as I mentioned, we look at individual elements of a system when we're doing our application analysis or our pen tests. We're usually looking at very specific things. We're either trying to exploit a specific person, say in the case of social engineering, you're dealing with one person at a time. You're looking at a single device if you're performing a pen test. Single device at a time, you might be iterating through many devices rapidly, but you're always really focused on a single device, or you're focused on a single action. The problem is when we focus on these single devices, these single actions, these single systems, we lose this rich interaction behavior between those devices, those systems, and everything else. And they just can't tell us about emergence, which means they're not going to tell us about emergent vulnerabilities. Now, we could try and replicate them in the real world, but that suddenly gets very expensive. How can you replicate emergent vulnerability? Well, you need the system that creates the emergent vulnerability, which might be a whole corporate organization. It's also not obvious from the interaction, so even if we could look at the interactions of a single application, we won't be able to determine the actual behavior of the emergent vulnerability from them. Why? Well, it's a bit of a circular definition. That's the definition of emergence. These simple interactions create this new novel, special, global behavior. So then how can we study them? If recreating them is really expensive, we need to find some way of simulating them or modeling them. Just like physicists want to study the universe, they have to create a model of the universe, because studying the universe with the universe is just impossible. So we have a couple examples I have here. I grabbed from sociology, the field of complex systems, and public health. We have the idea of epidemiology and agent-based models. Well, for the talk today, because we have a limited amount of time, I'm going to focus on agent-based models. And my reason for that is epidemiology is very useful, but you can actually have a number of epidemiology methods that rely on agent-based models. So this is a great foundation for looking at a number of complex behaviors. And I've seen them study the transient populations, economics, you name it, there's probably been an agent-based model to look at. So then how can we study emergent vulnerabilities with agent-based agent-based models. Well, what we do is each agent moves around in our system. They have individual interactions. They interact with each other constantly. They make their own decisions. You can think of it as artificial life. What we are trying to do is we're trying to simulate this organization, this, say, a corporation, inside our computer. You can almost think of it as artificial life. So now that I've gone through a lot of this high level of emergent vulnerabilities, how we can study them, say, agent-based models, I'll get into some meat and potatoes with a case study of looking at a real emergent vulnerability, how we studied it, what results we got from it, as well as some of the difficulties we discovered while we were studying this emergent vulnerability. In this case, the paper was back in 2010, published at a security conference, all about mobile location tracking networks. So, what is a wireless tracking network? Well, it's kind of like Batman. If anybody remembers that scene from Batman, you know, Bruce has decided he's going to hack every cell phone in Gotham and somehow turn it into a sonar positioning visualization system. It's kind of like that, but actually realistic. We actually started this project a little bit before that movie came out. So then what is a wireless tracking network if it's not exactly like what happens in Batman? Well, picture a botnet of smartphones. We've seen a few of these in the real world. Botnets of cell phones at least. Then let's put all those, that whole botnet, put them in a monitor mode. So they're sniffing the Wi-Fi packets and the probe frames and the underlying traffic as it flies across the air. And just look at those probe frames. We don't need anything else besides the probe frame, so we don't have to collect a lot of data. We just have to collect some of the probe frame information. For those who saw the talk yesterday about taking advantage of SSIDs, you can learn a lot just from the SSID of a wireless packet. And as we look at those probe frames, let's just record those SSIDs of the devices that connect to them. Or the BSSIDs of the actual devices, which are the wireless for MAC address. They can be used as unique identifiers. And every time we see one of those unique identifiers, let's send the GPS location where we were when we saw that MAC address. Send it to the command and control server. And then, say, every so often, that command and control server runs a job that takes all those GPS coordinates and unique identifiers and trilaterates them. Basically performs the exact same thing we do with 10 or 11 GPS satellites. So it looks something like this, to give you a bit of a visualization. We have an anonymous 9-block area. For those who are in BurbSec up in Chicago, we actually use downtown Chicago for our original simulation. And what we have is, we have a member of our botnet here, the gray circle. We have just a regular old person like you or me as our green circle, and we're walking around the city. And when there's just one little gray circle, one of our botnet phones monitoring us, when we're walking around, well, they only see us when we interact. So we're not giving the botnet a lot of information at that point. It's just one of them. However, here's where the idea of emergence comes in. So now, that's just a single interaction with 2 people. Now let's have 3 people in that botnet, these gray circles, and we'll walk around again. Now we're interacting with 3 different people. We're having all our devices interact. And then we walk through the city. And suddenly, at some point, as we have these 3 people, they're suddenly able to get a much better picture of how we walked through the city. So we go from just one, the botnet only sees us once, to now the botnet is seeing us 4 times as we're circling around these blocks in the city. And the emergence comes from the fact that, well, when we just have one individual in the botnet, or a small number of individuals in the botnet, they won't see us very often. It's probably not a large privacy violation. However, at some point, when we get enough people in that botnet interacting with us, we see enough interactions in our socio-technical system, we have a vulnerability. Our privacy has been compromised. They will be able to track our every move as we walk through a city. All because we just keep a phone in our pocket with Wi-Fi on. And of course, I want to be clear, we keep a phone in our pocket with a Wi-Fi on. We're not taking advantage of any vulnerability. There's no ODA involved here. We're just using our devices as they were intended to be used. So the question then is, well, how big does this network have to be for this vulnerability to emerge from these interactions? How well would such a tracking network perform? How well can it trilaterate these individuals if it just records our interactions every so often? And then what happens as we increase or decrease wireless broadcast range? Obviously, 802.11b won't be doing as well as 802.11g or 802.11n. And the other question, too, that we have to have about this is, this emergent vulnerability will depend on the city we're in, because the cultures in each city mean pedestrians and various business folk in the city move around in different ways. So this might be an emergent vulnerability in Chicago, but it won't be an emergent vulnerability in Bloomington, Indiana. So how do we answer these questions? Well, we need to simulate thousands and thousands of people. We need to be able to represent human mobility because we're trying to model a bunch of people walking around, and that's far cheaper than trying to capture a large number of people and force them to walk around a city while we monitor their every move. Probably more legal to simulate as well. We also need to simulate wireless detection, so we need to have these people carrying around devices. We need to be able to know when they see each other when they're within wireless range. And we need to determine how well folks can be trilaterated, how well their position can be narrowed down into a small square area. So, human mobility is pretty easy. Moving thousands of people is pretty easy. We just use an agent-based model. You could almost think of this as a very simple agent-based model if they randomly started walking around our 9-block square area. So we have our wonderful pedestrian people just walking around. Now we need to make them walk around realistically. And so there's actually this really cool application. I can show you the video offline as well if you want. The idea being there are people walking around, there's cars moving. What it does is it's simulating real traffic, it's simulating real people moving around a metropolitan area, going about their business, going into work, leaving work, shopping. You name it, they try and simulate it. And then we need to simulate wireless detections. Well, that's easy too. We've got Python. Everybody loves Python. It's great. We can whip up a script that takes the output of our mobility simulator and says, hey, look, we're going to make a slight simplification. We're going to say our wireless range has some radius, say 15 meters, 30 meters, 45 meters. Figure out what is a conservative value for the range of an 802.11 wireless card. And we'll just draw a square around each individual as they walk through that city that represents this conservative range and say, well, if anybody is in that square, we see them. And you do that for everyone in the population. And then finally, what you can do is you then have your wireless ranges and you draw squares around all of them. And then eventually you get enough squares, and in this center square here, we have a little blue circle that shows where our detections have overlapped. We've now gone from a much wider area to knowing, oh, well, now we know them. They're at the corner of that block. This also can be done with a Python script. It's great. And in fact, if anyone wants to talk to me afterwards, this code's on GitHub. I just don't publish the link here because documentation of code is iffy. It's well commented, though. It's very well commented. So what did we find out from doing all this? How did we answer our questions about how problematic this vulnerability was? We found out that you can track people a majority of the time if you only have 1% of the population in a botnet. That's all you need. And you can track people a considerable amount of the time. And the thing is, too, because you could say we are exploiting the nature of humans and their movements, they don't go very far between detections. And so even if you see someone 10% of the time, in between those detections, they don't move very far. They only move about 10 meters on average. And so you can very easily follow them as they move through the city because they're going less than a city block between detections. And here's the problem we have with this. As I said, all we are exploiting here is the idea that people carry around smartphones in their pockets with Wi-Fi on. We're not taking advantage of any exploit. So the solutions for this, while simple, turn off your Wi-Fi, aren't necessarily effective. Because if I'll tell you to turn off your Wi-Fi, suddenly the phone becomes not quite as useful, especially if you're hitting your data limit.
But you still have your cell phone on, and the cell signal does the same thing.
Yeah, yes, cell signal works exactly the same way. Oh, and for folks who are going to be using the new version of Android, even when you turn Wi-Fi off, Wi-Fi is still on unless you go back into yet another submenu and say, no, really, I want to turn the Wi-Fi off. Google is doing that to help provide you a better service for location positioning. And we could say, well, stop publishing unique identifiers in your probe frames. Change the whole way MAC addresses work. Try going to the IEEE body and asking them to do that. Let's see how much traction that standards change gets. We also found, as a side note, that Python circa 2009 was really, really slow for this. Its usage was about twice as long as Java. The trade-off, though, is when we switched to Java for the simulations, it suddenly took twice as much memory. So, go figure. There's also some difficulties in doing this research. You have to be very careful about how you generalize your results. As I said earlier, you have to choose very conservative wireless ranges, and I say you have to do this because if you don't, because you have to make some computational shortcuts, you can't draw circles, and we know Wi-Fi isn't an exact circle. We know it attenuates based on different, if it hits this wall versus this wood paneling, it's going to attenuate differently. And then suddenly, if you want to simulate all this, you're doing ray tracing, and oh man, your simulation is never going to run. So you make these simplifications. You need to be careful about what you generalize from these results. So for example, we only use Chicago. We can only really say something about Chicago because, say, pedestrians in Louisville are not going to move the exact same way as Chicago. The city is laid out differently. This completely depends upon the size of the buildings. We actually did this simulation for Dallas, and we get completely different results when we look at Dallas than when we look at Chicago. And the agent-based modeling in general, no matter what you do, is very susceptible to initial parameters. You have to get all your parameters as right as you can given the information you have. If they're slightly off because of the notion of emergence, if you have an initial parameter just slightly off, you can get completely different results in the end. But the rewards of doing this research is that we can provide some general risk assessment. We can say, hey, look, here's our vulnerability. I showed you how often you could be tracked. Is this a risk you're willing to live with? Is this something you're okay about being susceptible to? And then we can decide from there, is this something we really need to fix, or is it something we can live with? So what's happened since I did this research, it's actually really kind of cool. We published the paper in October of 2010. Back in 2011, we find out that Google's using every AP that its phone sees to help locate users. And then in May 2013, we start seeing that Nordstrom is using the Wi-Fi signals from your phone to determine what department you're spending the most time in the store so they can help improve the store experience. And that sounded almost exactly like what we talked about in this paper, but sadly, Lisa Voss from Sophos' Naked Security blog never contacted me. I would have loved to have talked about it. And nor did the New York Times, but I'm not really surprised there either, I guess. But we basically, 3 years before this actually happened, I'd argue we predicted that this was possible. So in conclusion, to end this talk, what are we going to do about these emergent vulnerabilities? This idea that we can have a vulnerability that really just depends upon our use of a device and just how we interact with each other. Well, we can simulate all the things, try and figure out, say, the interactions in our corporate BYOD environment, try and simulate this huge agent-based corporate model and see if we find any bad emergent behaviors. We really need to increase the knowledge of our security ecosystems. We need to document. We need to understand the interactions. We don't even know the interactions right now, so of course simulating all the things will be very difficult. And we of course have to get those initial parameters really well tightened down, so we need to better understand our security ecosystems to even do that. We can also globally monitor all mission critical systems. So Bro IDS, you basically have to monitor everything going in and out of your network, as well as all the functions that are currently operating on a system. So this is, of course, a very wide-scale, difficult logging problem. And maybe, do we need yet another life cycle process that people might or might not follow during a development cycle? Because I love the SDL, but I'd be curious to see how many companies have really built in solid SDL into their usual app development process. And there's some downsides to emergent vulnerabilities in that they don't trump current vulnerabilities that we have now. We're going to have to deal with current vulnerabilities, all this stuff that we're dealing with now that we come here every year to talk about and woefully say, man, we still haven't solved this security problem. Well, now we're going to have another one to worry about. But there's an upside to that. The upside is that we're going to have job security because there's more vulnerabilities to look at. That's awesome, I guess, in its own special little way. So finally, now that we've gotten to the end of the talk, what do schools of fish, ant colonies, and InfoSec have in common? Well, we all have to deal with this complex phenomenon now. Schools of fish, they interact with each other by looking at where their friends are in the school, and then they suddenly form these wonderfully complex circles and tornado shapes, and they avoid predators. Ants, based on what every other ant does, they're able to manage whole colonies of millions and millions of ants. Well, now in InfoSec, we have to think about vulnerabilities that are arising from us interacting with each other and walking around with our devices, all of this Internet of Things, and how this Internet of Things is interacting with us, and how this Internet of Things is interacting with the physical world. It's a lot to think about. And so we all have to deal with a little bit of complexity. Schools of fish are complex, ant colonies are complex, and now information security is complex. But hey, it keeps things interesting. And so if anybody has any questions, we've got a couple minutes left. We can also talk offline. Yes?
I have several questions, but I don't want to blow it past time. So the one that matters to the examples.
Uh-huh.
In the examples, you're tracking the device.
Yes.
Like the link between a device and an individual
Yes.
is not quite, I didn't see the link in the presentation. How's that handled without an old style model?
Okay, so the link between the device and the individual, I would argue in this case, you would either do, if you wanted to target a specific individual, you would have to do a bit of recon. The general notion, though, of this link is that people don't usually share smartphones. They won't trade smartphones. They will always have the smartphone on their person. So if you see a specific MAC address, you can probably assume that belongs to a single person.
But they change smartphones.
Every 2 years. Yes. So what you would end up doing is every time, you probably have some sort of attrition in your database every 2 years because you have to deal with people changing smartphones, or you have to redo your recon. But it's far cheaper in that case to quick redo your recon when they get new phones rather than tail someone constantly.
You just picked up the change from similar patterns in the system.
That, we were thinking about that. We haven't looked at that, but I think that is actually something you can do, because there's actually a research that was published in either Nature or Science a couple of years ago that showed there's not a lot of entropy in how we go to and from work and our daily routine. We stay really, for the vast majority of the time, our daily routine's constant. And so, of course, yes, if a MAC address changes, but suddenly we move the same way, we can correlate. Yes?
So a lot of what you're talking about was using Wi-Fi. I know that Bluetooth beacons is sort of taking off. What do you think about that?
So Bluetooth is definitely a problem. Wi-Fi at the time that we wrote this, Bluetooth, the Bluetooth hype had really died down. I'd argue maybe 2008, 2011, Bluetooth. At that point in time, the original Bluetooth phone thing had died down, the headset thing died down. There wasn't a lot of work going on because it's really hard to sniff Bluetooth packets promiscuously because of the device drivers, and a lot of cards didn't support it. At the time, there just weren't devices to do it, but on Wi-Fi, you can monitor Wi-Fi packets all day. So it was partly, we felt at the time, a more likely problem. But Bluetooth, any other wireless, any of this through-the-air transmission would be susceptible. We can take this offline. But thank you. Thanks everybody for coming out. If you have any more questions,